Okay, so welcome back everyone to NAS-IF Summer School Seminar last talk, which is actually going to be delivered by Nandan from Center for Theoretical Physics and Natural Philosophy or NAS, Mahidol University, Nakhonsawan province. So the talk title is about current tensions in cosmology. Nandan, if you're ready, please.
Yeah, I'm ready.
All right.
Thank you for the introduction, and good afternoon, everyone. So I would like to thank the organizers of the NAS-IF Summer School for giving me this opportunity to present my work in this school. So let us start. I will be talking on current tensions in cosmology. So what is the current situation in cosmology, and so the plan of my talk. Sorry. So I plan my talk in this way. So first few minutes, around half an hour, I will spend on the introduction to cosmology and current accelerated expansion of the universe. I will discuss about these two things, and next I will discuss about the current tensions in cosmology, and after that I will move to my own research, which is tracker behavior of the scalar field dark energy models, and we will be talking about two different dark energy model. One is quintessence, another is phantom, and then I will summarize my talk. And my works are based on these two published paper, recent published paper of mine. And if there is an image which I have not mentioned the source, so it is basically collected from the internet without any copyright. So just as a disclaimer. So let us start. So as I say, we will be talking about cosmology. So first, what is cosmology? So cosmology is the scientific study of the origin, evolution, and the ultimate fate of the universe. So these comes from the these things form from very ancient questions of humankind, and but here we study scientifically. So these are the main motivation for cosmology to study. But if you want something specifically in which the question in which cosmology is more interested is how the universe has begun, you can split the question more scientifically, and how it evolved, and what are the components of the universe, and how old is the universe. So, and what will be the future of the universe. So these are the questions in general we ask in cosmology. Now to start with the cosmology, to study the cosmology scientifically, we generally start with the principle which is called cosmological principle, in which we say that the universe is homogeneous and isotropic, but we have to mention this is it should be for large scale. So on large scale the universe is homogeneous and isotropic. So the picture on the left, you can see this is an example of an isotropy, but it is homogeneous. So you can take a square box in everywhere and you will get the same number of lines, but here these are the concentrated circles. So here around this center, wherever you look, it looks same, but here actually if you look different in different angle, it looks different. So this is anisotropic but homogeneous. This is isotropic but homogeneous, and but inhomogeneous. But what cosmological principle says is that our universe is both homogeneous and isotropic, means there is no preferred center of the universe and there is no direction. So each and every place of the universe is same. And what it actually means more scientifically is that the laws of physics are universal. So it is true for everywhere. So now as I mentioned, it is on the large scale. So how big is the large scale? How does it means? Means let us start from the our Earth. It is not homogeneous or isotropic. So you can look around yourself. It is not homogeneous or isotropic anyway. Even if you go to the solar system, the sun is there, and if you there, it is not homogeneous and isotropic, you can say. So from solar system you can go to the interstellar neighborhood, and even if you can go to the Milky Way, and from Milky Way you can go to the local galactic group. When the galaxies they make a group, and from the local galactic group they make the supercluster. If you go to even our supercluster, that is Virgo supercluster, and it is not homogeneous and isotropic. Then if you go to the local super cluster, it is still not. But if you go beyond that, which is the last one, here you can see it is homogeneous and isotropic. It's like you go inside, you will see everywhere looks same and everywhere have the same property. So as I mentioned, it is on large scale. The principle of homogeneity and isotropy is that is the cosmological principle is true. The next is we call this Olber paradox. So now we know that our universe don't have any center or any preferred direction. Now we can ask about is our universe is infinite in size, or it is infinitely old. So there is a paradox that is called Olber paradox. So suppose if our universe is infinitely old and it is infinite in size, and the stars are there, then the night sky should not be dark. Why? You can understand from here. You consider this forest, dense forest, and if you go inside this forest and you look, if this is an infinite forest, and you look around any direction, your eyesight will go and hit some tree. So what you will see? You will see a background of trees around you. So similarly, if you consider this is our universe, and it is infinite. So if you are here and you look around any way, so you will get your sight of you will hit one star somewhere. So if you mathematically integrate it, so you take a spherical cell of R and R plus dr, and this is the flux, and if you integrate simply, you will see that the luminosity is going to be infinite. So that means the night sky should be infinitely bright, at least as bright as the surface of a star. So that means, which is not true, we see our night sky is dark. So that means there is something fundamentally wrong about our assumption that the universe is infinitely old or infinite in size. So what is the resolution for this? The resolution is that the universe has a finite age. So the universe has a age. So the light from the stars after a finite distance has not time to reach us. Means there is a boundary beyond which the stars, the light from those stars, till now had no time to reach us, and this distance is called horizon distance. So what we find from these two things is that our universe don't have any preferred center or direction, and our universe is finite age, and we have a horizon distance beyond which we cannot communicate. So before the discovery of the general relativity, generally the cosmology was a subject which was more discussed in theology or in religion. But after the discovery of Einstein general theory of relativity, it has become a part of the basic pure science. You can use the scientific methods to study, and so we have, for that we briefly spend some time to understand the difference between the Newtonian gravity and the Einstein gravity, and what Newton's so let us start from the Newton's law of gravity, which says that the any two objects in the universe, they attract each other, and the force of attraction is defined on this mathematical way, so you already know it. And the second law, Newton's second law, which this is the law of gravitation, and this is the second law of Newton, which says the force is proportional to the acceleration. So there could be a proportionality constant, and you can call this the mass. So now you can see that this mass, this is called generally the inertial mass, and this is called the gravitational mass. So they might not be same, but if we found the acceleration acting on a particle of A like this, so the F, so you put this F, so there is a force due to the gravity. Now that force create the acceleration. That acceleration is going to happen according to the law, or second law of Newton, in which the mass is the inertial mass, and for the gravitation, the mass is the gravitational mass. And then you basically, when you write, if you remember from your bachelor classes or high school classes, you just cancel these two, and they are basically, there you actually assume one principle, which is called equivalence principle, in which the gravitational mass and the inertial mass are same. And you can do the experiment. The first experiment was done by Galileo, and you can do the modern days experiment, and you can show that this ratio is of the order of 10 to the power 12, means is highly accurate that these two are same. And Einstein took this idea that the gravitational mass and the inertial mass are same, and he performed this thought experiment, in which he put a person inside a spacecraft which is accelerating with an acceleration g, and the same spacecraft is standing on the surface of the Earth. So now if this spacecraft is accelerating with an acceleration g, then this guy inside, if he or she don't have any information from the outside, cannot differentiate between if he is on the surface of Earth or it is actually accelerating. So then further he extended this idea. So suppose there is a torch here, and if you put a light beam, if you switch on this torch, and this frame is accelerating with the acceleration g, then this light is going to bend this way. So from there he also got the idea that near the mass, near Earth also, if you switch on the torch, the light beam also should also bend in a similar way. So that means so what Newton say is that the mass tells gravity how to exert a force, and the force tells gravity mass how to accelerate. So if you have two masses, so these two masses say how to exert a force, and the force actually tells the masses how to accelerate. So this is the Newtonian way. And what Einstein say, that the mass and energy, it actually bend the space and space-time, and or curve the space-time, and any mass actually follow that curved space-time. So mass energy tells space-time how to curve, and curved space-time tells mass energy how to move. And one interesting from this sorry, I just forgot this name. So here you can if you ask someone that suppose there is a cart here, how it will move, and so if you say answer in Newtonian way, you will ask about all the forces acting and the initial conditions. From there you can calculate that how it will move if there is a cart here. And now if you want to give answer in Einstein way, you will just say it will follow the track which is already given here. So this is the Einstein also say that the movement of the any object will just follow the space-time curvature. So after discovering his general theory of relativity, Einstein tried to apply it to the universe, and he believed in a static universe, and he basically, in the previous one I'll discuss later, that you see this this lambda, which is called cosmological constant. He actually introduced this to get a static universe, to balance the, because if there is gravity, so it should not be stable, to it should collapse. But he put this lambda term, which is I will discuss more later, that to make a balance between gravity and expansion, so that you can get a steady universe. But in 1929, Edwin Hubble was observing galaxies, and he was plotting the redshift of the galaxies with the velocities of the galaxy with the distance. And what he found, actually, he found that the farther away the galaxies are, they are moving away from us with greater velocities. So that means each and every galaxy, they are moving apart. And this is the famous Hubble's law, and he gave this simple linear law where the velocity of recession is actually some constant into the distance. So after this discovery, Einstein rejected his idea of the cosmological constant, which I'll discuss more. So now you got the idea that the universe is not static and it is moving, and you can, in mathematical way, you can write this redshift like this is the same as you used in for Doppler shift, and this is the lambda observed minus lambda emitted by lambda emitted. So if this is z is less than 0, so it is blue shifted, is greater than 0, so it is red shifted. So if you put this here, so you can just derive mathematically also the Hubble law. So that means the galaxies are going apart from us. So now what is happening? What is we have to think that our universe is actually expanding. Our universe expanding is like, you can roughly think of a expansion of a balloon or a ball. On the ball you have some bugs or dot, and as the balloon or the ball expands, so the balls or the balloon, the dots or the bugs, they are going away from each other, and which does not mean that one is going to, if something is going away, that means that thing is going to come towards something, but everyone is going away from each other. That means the space inside them, the distance itself, the space is increasing. So so is it violating the cosmological principle? No, it is not violating, because it is the expansion of the space itself. And one interesting question might be, is there a center for this expansion? No, again, there is no center. Everywhere the space is itself expanding. And now another interesting question, that if two objects, so we say that the velocity is proportional to the distance. So if can it happen that the distance is so large that the recession velocity, they go apart, can can go beyond the velocity of light. Yes, it can happen, but is it allowed from the special theory of relativity? Is it violating the special theory of relativity? Actually, it is not violating, because you are not sending a signal, which is for signals actually the velocity of the signal cannot go more than light. But here two objects is going away from each other. It can happen they have the velocity with respect to each other more than the light, and this is because the space itself is expanding. So this is possible, and this is not violating the special theory of relativity. Now, as I have mentioned, that the galaxies are flying away from each other, and which actually means if you rewind them, so you can think of them that once upon a time they were all clumped together. So suppose these are the two galaxies, they are going away r. So V is h naught into r. So you can write a time coordinate here, t0, that is r by v, and you can see that there is a natural measurement of time, which is the inverse t0, which is inverse of the Hubble constant. And this is roughly the age of the universe. This is not exactly, because this is roughly the age of the universe. And you can also find a distance beyond which the recession velocity is more than c, which is physically allowed, but what you cannot go. So you got a distance beyond which the galaxies are moving away greater than c. So what you can get is that the restriction you get, that you cannot contact with those galaxies because they are going away more than the velocity of c, and that you can calculate is roughly 4300 plus minus 400 megaparsec. And if this is the scenario, then you can think in the past all these things, you can rewind the time, and you can say that all these things were clumped together, and which is generally called a Big Bang model of the universe. So the universe have started from a very hot, dense, and a very small, hot, dense phase or situation. And now we discuss about the components. What kind of components we can have in the universe? We can have we can define them in three main categories. One is the non-relativistic components, another is the relativistic, and another thing is the dark component. The non-relativistics are proton, neutron, and the electron. And the relativistic components are neutrinos and the photon, and the dark components are the dark matter and dark energy. And as you see the budget here of the universe, the dark energy actually can have around 69% of the universe, the energy budget of the universe, and dark matter has 26, and the rest of the 5% is basically by this neutrino, proton, electron, neutron, proton, so and photon. Sorry. So this is the component. These are the major components of the universe. And I should not talk. I thought about the dark energy. So what is dark matter? Dark matter is a kind of a matter which basically does not interact with the electromagnetic radiation. So you cannot see the dark matter. Like here is the normal matter. So if electromagnetic signal passes, so it will interact. This matter will interact with it, and you can see here, or you can also see it from here. But with the dark matter, it just the signal passes just as it is. So if that is the case, so how do we know that there is dark matter? Because we get the we can detect them indirectly by observation, by observing the rotation velocity of the stars in a galaxies. And if you see that, if you have a theoretical model, and you see that the rotation velocity of the stars with the distance from the center of the galaxy, it first increases, then it goes to the maxima, and then it should decrease. But rather, when you observe, you see something like this: it increases and it goes, and it becomes almost constant. So this says that there is something which makes this velocity of the stars with respect to the center to be constant, and you can see that is called the dark matter. So every galaxies have a dark matter halo around it. That causes this. And you have many other observations like the gravitational lensing and other observations which you can confirm the existence of dark matter. Now let us discuss a few minutes on the Big Bang cosmology. And as you know that our universe has started from a very hot, dense situation, small point, and then it started expanding very rapidly, which is called inflation, and then it actually slows down, and it goes through different pages of the evolution of the universe, in which the stars form, and the first you got the elementary particles, then you got the structure formation, and basically you see the universe as it is today. But what happened in recently, the universe, as you can see, that the slope of this one had increasing. The slope was kind of getting down, is negative, but you got an positive slope here. That means the universe has recently means in terms of in age of the universe, has started to expand, accelerate. So this is we are going to discuss in more details. And here is the detailed description of the chronology of the universe. So the universe started with singularity, and there will be inflation and the baryogenesis. So 0 to 43, around minus 43, is called Planck epoch, and where the four fundamental forces were unified. And then around 10 to the power 37, a phase transition caused the cosmic inflation, and in which the universe actually grew exponentially, and then actually reheating started, and the quark-gluon plasma and the elementary particles formed. And then the universe slowly cooled down, and you got the baryons like proton, neutrons, and from there you got the structure formation in the universe. And the current stage is the cosmic acceleration of the universe. Now, if you want to find, if we want to make cosmology as a science, then we have to formulate the one thing, the mathematics. And the first thing we have to start with is the measurement of the distance. And as you know, the measurement of the distance depends on the on the surface, like the curvature of the surface. So if it is a flat, you got a one kind of measurement. If it is a curve, and the two most simple curve cases are this is positively curved, so you measure the distance on the surface of the sphere, and another is the negatively curved, which is like a horse saddle, if you have seen, and this is called negatively curved. So for the flat, what is the property of a triangle? The sum of the three angles are actually pi. So this is actually, and the distance dA square is dx square plus dy square. And in the polar coordinate, if you consider, you can write dA square is dr square plus r square d theta square. This is very basic. And if it is positively curved, so the sum of the three angles actually is more than the pi. So it's depend on the r, the radius of the of the sphere, and then you have the formula between the distance of 2 points, which is like this. You have this sine square r by r d theta. This is very easy to prove. And for the negatively carved, the sum of the angles, sorry, this alpha beta has been misplaced, so this would be alpha beta and gamma. The sum is less than the pi, so you got a distance formula like this. Now you can extend this to a three-dimensional case, where you increase one more coordinate and it will look like this. These are very common and it's familiar. And now you can put these three in a single formula, and where S, K, R, depending on the curvature, can take this form: R sine R by R, and R sine H R by R. So in terms of in general relativity, we generally call this as a metric. And as if you remember, in four-dimensional spaces, where if you consider the time to be another dimension, you write the Minkowski space, the metric for the Minkowski space like this. Now, if you want a universe as a spatially homogeneous and isotropic, if you want to implement this condition mathematically, and if you want to allow the universe to be expand or contract, so you have only one choice, which is the called Friedman-Robertson-Walker matrix, which looks like this. And this A square T is basically called the scale factor of the universe. Scale factor means it decides how the space is increasing or decreasing, the evolution of the space itself. Now you got the Friedman metric, and you got the Einstein equation. You put this Friedman metric, use this one in the Einstein equation, and you will end up with three independent equations, which are like this: a dot by a square equal to this is called Friedman constraint equation. This is the acceleration equation. So this gives you a constraint on all the component the energy density of all the component of the universe, and this gives you the information about the acceleration of the universe or deceleration. And this is the evolution of each component of the density of the universe. Now, as you see in the previous slide, you have four unknowns like P, rho, A, and basically you have and you have three equations. Now you have to consider a relation between P and rho, which is called the equation of state. So we generally call it P equal to P as a function of rho, which is called a barotropic relation, where you just put a W here, and if the component is matter, so there is no space, so the W is 0. If it is radiation, then you got P equal to 1/3 rho and W equal to 1/3. This is an example, but if you have another component, you have to define their equation of state, which we will see soon. Now you got some idea about the basic cosmology. Now the thing is, our universe is actually, as I mentioned before, accelerating here. As you can see, you got some positive slope. So recently the universe has started accelerating. In 1998, two different independent groups, they were studying the supernovae, and they found both of their results suggested that the universe is actually accelerating. Apart from these supernovae, there are evidences like the age of the universe and supernovae itself, and the CMB and the Baryon acoustic oscillation and large scale structure, and you have other observations also, which suggest that that the universe is actually accelerating. So it is confirmed by multiple independent observations. So let us consider the age of the universe. How does it conform the accelerated expansion? So this is the evolution of energy density. You might have already encountered this in your cosmology class. And from here, you can calculate the age of the universe. And here, by this way, actually, you can insert the density of the different components of the universe in your calculation of the age of the universe. Now, if you do not consider the contribution from the dark energy, what you will find, the universe is younger than the last star, than the oldest star. So that is not like mother is younger than the baby or like that. So that's not possible. So the universe has to be older than the far star or the oldest star. So for that, you can see this is from the observation. So here you can see you have to consider that omega m to be somewhere here is around 0.3. So the rest of the thing is some unknown kind of energy. Otherwise, you will end up here where the universe is younger than the oldest star. And now the observation from supernovae itself, it is from the type 1a supernovae, in which basically what you can see that the type 1a supernovae happens when there is a binary system of two stars, and one is actually form an accretion disk by attracting matter from another one, and now the matter goes onto this white dwarf, and it increases its mass, and there is a threshold which is the Chandrasekhar limit, and in the star burst, and it's create a huge luminosity, and that is quite independent of the history of the star. So wherever it happened, so it don't remember how actually the initial star was. So if the energy content, the matter content increase the Chandrasekhar limit, so it just explodes. So this is used as a standard candle to measure the different quantities of the universe. And here you can see these are the data for this is called the luminosity distance, DL, and this with respect to the redshift. And here you can see this, the green one. You can best fit the observed supernovae data if you consider the omega lambda or the dark energy to be 0.69. Otherwise, if you consider the omega lambda to be 1, so this is overshooted. If you consider omega m to be 1, so this is undershooted. So you have to consider this is the best fit for this curve. And now I think you already know what is CMB, and from the CMB also you can confirm the accelerated expansion of the universe. And CMB is basically background radiation which is present every direction, and it was detected by the Penzias and Wilson in 1964 when they were experimenting with some super sensitive radio antenna, and they got an signal all over the sky. And they have some interesting story about the pigeons here, and which says so. And after that discovery, and if the Big Bang cosmology is true, so this is one of the most profound proof of the Big Bang cosmology, that at the beginning the universe was a kind of a soup of energy, and then you have a state where you have the electron and the photon, and the photons, they move, but they are blocked by the electron, so it was opaque, and the universe actually expanding, and the photons are losing the energy, and suddenly at a point the universe became transparent and the photon moves, and this till now you can see this phenomena as a background radiation, which is something like this, which is called the last scattering surface, because we have to remember when we see far deep in the space, we actually see our past. So if you go more, you can see that the remnant of that state as a background emission of background radiation, and which is like this cloud. So if you see on the see to sky now, you will see at the bottom of the sky. So that is like that. So you cannot see beyond that. So since I say that the CMB is everywhere, it is homogeneous kind of it is, but there are some fluctuations, and you can measure the correlation between the fluctuations, and from there you can also calculate what is the best fit for the different values of the cosmological parameters. And here also it can also confirm you that you have to consider the dark energy to be around 0.69 or 0.7 to best fit the data from the CMB. And you got the another one is the BAO. BAO also has this is the Baryon acoustic oscillation. This is the phenomena in which basically the universe was having the baryons, electron and photon plasma with the dark matter, and some inhomogeneities form, and the overdense region form, and the dark matter actually attract all the components, the baryons and the electrons, and they fall onto the dark matter over density. But there were also the photons; they are coupled to the electrons, and there were so when the electron proton and they fall to the baryon over density, so the electron the photons got the radiation pressure. So there was the oscillation between this one. But at that time the universe was also expanding. So what happened? Suddenly the universe expand and the photon decouple. So you got basically a cell of the baryons, which is like this. So this is the over density where you got a cell of the baryons like this. And this is not the original. This is a kind of animation here, and this is the real slogan digital sky map survey here. And you can use the statistical tool to find a correlation between the galaxies, and it says that about co-moving separation about 110, you should get the correlation function should get a peak, and you can see this is the observed peak, which is the observed phenomena, and you can see that this is also best fitted when you got the dark energy to be 0.69 or 0.7. Even from the large scale structure, because the large scale structure they gives you the information about the expansion of universe or the evolution of the gravity. So as far you see in the universe, the large scale structure, you see how they were the gravity or the evolution of the universe were at that time. So from there also you can basically confirm that accelerated expansion of the universe. Now I have to try to convince you that the current phase of the universe is some weird phase in which the universe has accelerated expansion. And suppose if you know all the known matter, what you know, if you try to explain the accelerated expansion with the known matters, you have more detailed knowledge, you cannot explain it. So it is a phenomena which is kind of opposite to gravity. So gravity will always try to slow down the process of expansion, but here it is actually getting faster, so accelerating. So as I mentioned, that Einstein introduced this concept of cosmological constant, which is inbuilt in his theory of gravity. So, but he abandoned it. His motivation was to stabilize the universe, because gravity will try to slow down or the collapse, and he tried to put this lambda term to balance between these two. But here, after the discovery of the accelerated expansion, it becomes that you can use this lambda to also accelerate the expansion. So that's why the lambda re-entered the scenario after the discovery of the accelerated expansion as one of the major explanation for the dark energy or the accelerated expansion. So what is that? So since you know that this is the conservation of the energy momentum, and this is the identity of the G mu nu. And if you want, you can put a lambda G mu nu term very without any loss of generality in Einstein equation, and you can just put it here, or you can start from this action, and you can find this equation also. And if you consider that Einstein equation with the cosmological constant, and now you apply the Friedman equation, now you consider the basically the FRW metric. You got these three equations. This is the Hubble constraint equation, and this is basically the accelerated expansion equation. So previously you don't have this lambda here, and this is the lambda here. So as you see that this lambda term is 0, that means the acceleration or deceleration only depends on this term. And for acceleration to happen, you have to get that this rho p by rho should be less than minus 1/3. And now if you put a lambda by 3, so you got a positive term to balance this lambda, and even you can overcome this negative and accelerate this one. Yeah, and the final motivation behind Einstein was to make this term 0, because he wanted a static universe. But this is very unstable. You can go to any textbook and check. This is very unstable situation. But as I mentioned, this lambda in recent years is the best choice for the accelerated expansion, because you don't need anything very complicated with a very complicated mathematics. It's inbuilt in the Einstein theory of general relativity, and you can explain the CMB, the cosmic microwave background very accurately. And these table shows the data by considering the cosmological constant as the component for the accelerated expansion, and you can see that you can feed the data with these error bars, which are very accurate. So the fit with the cosmological constant is really high. So this is the one of the best choice as the candidate of the acceleration expansion. And these are the kind of plots, as you might have already know about this kind of plots, which gives you these plots actually related to this table. Now, if the cosmological constant is there and it can explain the observed data very precisely, so what is the problem? The problem is when you ask the question, what is the cosmological constant? And if you see, this is the property of the space itself. So what we have in our quantum field theory is that the property of the space is, you can consider it as the vacuum energy, and you can try to calculate using our knowledge of quantum field theory, what should be the vacuum energy density. And you can see that what you calculate from our knowledge of quantum field theory and what you observe has a mismatch of the order of 10 to the power 120 or 121. Now, if you go to the string theory, you can lower down it to the kind of 10 to the 74 or something like that. But still, it is one of the biggest mismatch between the theory and the observation in physics. And cosmological constant gives rise to another major problem, which is called cosmic coincidence problem. So the cosmic coincidence problem is, which says that the energy density of the dark energy and the dark matter, they are comparable today. So dark energy is 0.669 and dark matter is around 0.26. So you can see these two numbers, they are comparable of the order. So, but if you see the history of the universe, is like at the beginning they were not comparable, because the ratio between them were almost zero, d omega lambda, and then suddenly you got a kind of a delta function, and then in the future they are going to be again very small, the ratio between then the question is why now they are comparable to each other. And if they are not comparable to each other, you will get many problem with the structure formation and like that. So which is called the cosmic coincidence problem. And this is not only the cosmological constant, this problem is suffered by many other, almost all dark energy models except few of them. And you can frame this problem in a different way, that to get the universe what you see today, you have to fine tune the initial condition to be very precise at the beginning, which is also kind of an absurd phenomena, which the cosmological constant is plagued with. Now, these are the these two are the very well-known problem with the cosmological constant. But very recently, within couple of years, another interesting phenomena is, like you can see, it started around 2012 or 13, and another interesting phenomena which arises is called the Hubble tensor. So as I mentioned in the beginning, that the Hubble parameter, the current value of the Hubble parameter H0 is very crucial for the cosmology to study the universe. So you can measure these in two ways. One is the direct way, in which you actually measure the nearby objects, and with the nearby object you measure the distance and their velocity, and from there you measure the H0. And another is, you have another experiments like CMB, BAO, BBN, means the nucleosynthesis data, and all these are the early time data. So when you see the universe in one hand, the nearby object, that means they are late time. So you are seeing the late time universe, which is very close to our time. And when you see CMB, it is the early time data, even the BAO also. So from there you can estimate H0, and here you can measure directly the H0 or H0. So this plot actually suggests that the blue one is basically called the distance ladder. Means these are the methods in which you measure the distance and the velocity, and you calculate the H0. And this red one is basically from the CMB. This is W stand for the W map, and this is the Planck, this is the BAO, and this is the Planck 18. For what is happening in the previous is around 2005 or until 2010, the experiments were not accurate enough. So you got an overlap between your measurements. So from until here, you can see that the measurement of H0 between these two different independent ways have an agreement. But when our precision of the measurement of H0 improved, what happened is that you see they two got separated to different branches, and one suggests that this distance ladder method suggests that the age naught should be around 73 to 74, and the early time data like BAO and CMB, it suggests it should be around 67, like that. So it is completely these two data set disagrees now. Now, what is the problem theoretically? For BAO and CMB, we see that I have already shown you that the cosmological constant fit the data very accurately. So that means the physics of the late time might not be cosmological constant. It might be something different than the candidate might be different from the cosmological constant, which might behave at the early time as cosmological constant, but might have some other behavior which shown up in the late time. So this is another tension, which is very ongoing tension, and it is an open problem also. And another tension which is also found about the sigma 8, which is called which actually measures about this structures of the universe, where you can find that this is the measurement from the CMB, and these are the other measurements, and which say that this measurement and the other measurements, they don't have agreement. The CMB measurement of the sigmoid quantity and other measurement of the sigmoid quantity, they have also an disagreement. So this is another problem which is called the sigmoid tension. So what I try to motivate here with these problems with the cosmological constant is that now we have enough reason to think beyond the cosmological constant. So what could be the approach? Alternatives approach for the cosmological constant. One might be the modification of gravity, and in which you take the Einstein equation and you change the gravity part. Another might be the modified matter model, in which you change the matter. So either you change the theory of gravity or you change the component of the universe. So these could be the two different ways of explaining the accelerated expansion. And within the modified matter model, the few names are like quintessence, phantom, and Chaplygin gas, and the K-essence. These are the names. But today, from now onward, I am going to enter to my own research topic, in which I will be talking about this quintessence and phantom model in a particular class of solution, which is called the tracker solutions. So what are the tracker solutions? As I already mentioned, that with the cosmological constant, there is a problem with the coincidence. There is this coincidence and the fine-tuning problem. So one can find a tracker solution, which is called the tracker solutions. Means they are kind of an attractor solution. So you got these solutions, it goes like this, and you basically start any other solution from any other point with a different initial condition. So a bunch of initial condition can converge to a common evolution track or the solution, and which solve this problem with the fine tuning. Means you can have a large number of initial condition, but effectively the evolution after some time is going to be the same. And what we try to do in this work, that in the literature there was previously people actually explored this idea of tracker solution with the different potentials, in which they did not find an accelerated expansion which can match the observations. But in these two works, which I'm going to explain, we find a general class of tracker solutions, in which you can actually explain the accelerated expansion of the universe and also satisfy the observed data. So mathematically, tracker models are those for which the equation of the dark energy is proportional to the equation of the background. Background means so the dark energy equation of state of the dark energy, and suppose you have dark matter and you have radiation and dark energy. So at that time, the radiation, the equation of state of the dark energy is proportional to the equation of state of the radiation. And as you see, all the components, it goes like this. The evolution of the component goes like this. And if you got a connection between dark energy component and dark matter component W, and then you can solve the coincidence problem. This is also possible because the tracking solution actually solves the coincidence problem. So you can visualize this here. So this is the radiation, how the radiation density of the radiation as the universe expand decay, and this is the matter, this bold dot, and this is the Q field, means the tracker field, and this is the region for which wherever you start the solution, you can see this is the 100 order of magnitude for the initial condition. So you can take 1 and 100. It gives you, after some times for J, all these solutions, they go and march to a common track, and that is called a tracker solution, because all the other solutions here, they track they are attracted to these solutions, and the tracker solution actually tracking the background, as you can see. So when radiation was dominating, it was almost tracking the radiation in the same in a same type of evolution. Then it started to track the matter. Now it actually overcome the matter. So the tracking solutions actually solve these two problems. One is the fine tuning, and another is the cosmic coincidence problem. Now I go particular to the quintessence model related to my research. So for the this is the effort W metric, which I have already mentioned before. This gives you the homogeneous and the isotropic universe, and we are considering this K to be zero. That means the universe is flat, and this is the action for the scalar field, and this is the Lagrangian. You have to do the mathematics, and you can find these are the four sets of these are the four equations. The first three comes from the Einstein equation, and this one is the Klein-Gordon equation, or that means the evolution of the scalar field itself. Now, as you can see, this H for the Hubble parameter, rho and P, there the density, pressure, phi is the field, and V phi is the potential with the quintessence field. So this kind of scalar field models, you have a potential, and the field actually roll down the potential, and it can generate the accelerated expansion, which have already been well studied. Now you define you will, if you calculate the density of the scalar field, you can calculate it in this way, like half pi dot square plus V phi, which is like energy, and the pressure is half pi dot square minus V phi, and W phi will be P phi by rho phi, because we have already mentioned it, and we'll be using another notation for the equation of state, which is W phi is equal to gamma phi minus 1. Now, one interesting thing is here is that you got the four equations, four unknown, but the problem is you got arbitrary thing, which is the potential. You don't know what should be the potential look like for the scalar field, and this is a big question. So to know what should be the potential we will be studying, you can do one thing is that you can transfer these coordinates by using a transformation, which is called autonomous to form an autonomous equation. So you can consider x to be this, y to be this, and y1 and y to be like this. these are the 4 parameters. So this is also have some polar component, as you can see, sine and cos. And with a bit of mathematics, from here you can write that theta prime is this y1 prime and omega phi prime. So you got a set of autonomous equations here. And this prime means it is derivative with respect to the n is e-folding. And as I mentioned, that we'll be using the gamma pi. Gamma pi is 1 minus omega pi, 1 plus omega pi, which is, and omega pi can be written here as the cos theta in terms of minus cos theta in terms of this polar variable. Now, as I mentioned, we have the arbitrariness of the V phi. Now you got the arbitrariness with the Y2. Because as you say, you got theta, y1, 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 but only y2 is not known. So how do we calculate y2? We can calculate in 2 different ways, that you can consider a V phi and use this definition to get a y2 from here. Otherwise, you can consider y2 and get a potential form of the potential. These are the 2 different reciprocal ways you can do. What we actually did in one of our previous work, couple of years back, we here around. So we actually consider different potentials which are most popular in the literature, and we find out y2 for all of them. And when we find out y2, interestingly, we found that there is a pattern in y2 for all of them, and you can write them in generally as a power series for the y2 is y into y1 y. This is the power series. Now, if you consider n equal to 2, you can get back almost all of the potentials. Now, what we can do, we can vary these alphas. So this is for I equal to 2. So you can write this way. Now you can vary the alpha, and you can got 8 independent combinations. With these 8 independent combinations, you put, suppose the first one, you put alpha 0, alpha 1, 0. So you got these two 0. Then you integrate these two from this definition, you can get a particular form of the potential. And interestingly, all the potentials here is the subclass of here. So you can get back all the potentials from where actually the main form is generated, and you can get these more general classes of the potential. So this is to show you that that we will be considering y2 to be this, and as you can see that by considering y2 to be this form, we are considering a large class of potential to study within a single umbrella. And this is the same thing which I already mentioned. Now you got the y2, which is this, which contains a lot of potentials with their subclasses also, and you got these 3 equations. You can put this y2 here, and now you can find out the critical points or fixed points. The critical points or fixed points are the points when you make the theta prime, y1 prime, or w phi prime 0. That means if you remember from the calculation of your maxima or minima of a function, where you have the function is basically stationary, means you just make the time evolution to be 0. But if it is a stable or unstable maxima or minimum, that means maxima or minima, that's a different question and need more analysis. But here you just if you make all these 3 equations to be 0, you can got these 4 class of solutions. One is the fluid dominated solutions. Fluid dominated solution means it's matter dominated, means you got at around this solution, this point, you got this point in which the dark energy density is 0. So it is only matter is there. And what is that? Could it be a physical situation? It could be, because at the very beginning of the matter domination or matter dominated era, it was almost this fixed point can almost mathematically satisfy. Next, you got another class of solution which is called scaling solution, where actually the equation of state is equal to the total energy gamma total. Gamma total is the sum up of the all the equation of state of the components, and the gamma phi actually vary with respect to gamma total. And another is which we are interested in, the tracking solution is in which the equation of state of the dark energy is proportional to the equation of state of the background, or means the total one. So you could have another option where you have only the quintessence energy and there is nothing else. So from this is mathematically you can find all this from here. Okay, so now this is the tracking solution which we are getting for, if we put from in this equation that alpha 0 and alpha 1 to be 0, you find that the gamma phi is proportional to gamma total. Here the proportionality constant is -1/2 alpha. And can you do it for alpha 0 and alpha 1 to be in general? Yes, you can do. You can show it, and where you can see that if I make alpha 0 and alpha 1 to be 0, so this term and this term is 0. Now if I basically consider a situation where omega phi was very small, then also you can go at a similar tracking behavior. You don't have to consider a particular choice, but we consider this particular choice, and from this particular choice you can study so this is the condition for this fixed point to be exist, that alpha 2 has to be less than minus gamma total by 4, and if we want the tracking behaviors to start at the very deep in the radiation domination, then this alpha 2 will be -1/3, less than -1/3. So let us consider this example. As I mentioned, from the table before I showed, you can get a potential which is like this, and where you can write this P in terms of alpha 2 because your other two alphas are 0, and you can write this gamma phi this way, and alpha 2 is less than 1/3. This is the constraint you can put from the previous knowledge of this, and the existence condition can be translated into P in this way, which is a very small and simple mathematics of inequalities. You can just show it. And as I already mentioned, that it is possible to show you that the tracking behavior can be true for a general class of potential when the alphas are not 0. Now, what we have also studied the linear perturbation of the system by considering in a synchronous gauge. So this you define two different variables like the dynamical system we form for the background, and you can consider another set of transformation, and from here you can see that the two different dynamical equation can emerge, and this involves lots of mathematics and calculation, and this kj is the Jeans number. So now what we are interested in, we are interested in to show that if we can put this one in some code, some code which can simulate the cosmology, and we will be using here is the called Boltzmann code, which is class. And for the class we need to, because this is where you are solving, you are going to solve the differential equation numerically. So you need to put some initial conditions, and we actually use the tracking condition here to find the initial conditions. Again, you have to do some mathematics to find that the initial conditions are like this, and we consider the linear condition for the perturbation quantity. to be 0 to start with. So this is actually the plot of the evolution of the equation of state, and this black one is basically the omega is 1/3, and this is for the omega pi is around matter domination, and you can see that the value of the equation. So you can see that this here are lots of solutions. At the beginning they were almost same, so they started from different conditions, initial conditions which we make in the class. Then you can see here actually they were moving like the same, and then at late time they got different evolutions. Sorry. Okay, so here is a phase plot of equation of state and the equation of state prime. So this is the radiation domination. So around radiation domination, and even when we start the solutions, they were almost evolving similar pattern. Then when almost matter domination, they have their behavior got differentiated, because you have to remember that the initial problem with the initial condition is very deep in the radiation or beyond the radiation domination. So until even in the radiation domination, these solutions they have a common track. So that's why we have the tracking solution. And we consider this the plot of the perturbations. So as you can see in the previous, I mentioned about in the when I was mentioning the CMB, and these are the here you choose the alpha 0, alpha 1 and alpha 2, three different alphas. You got different set of solutions, and here we also showed the different set of solutions, and you can show that the perturbation actually quite affected by different choices of alpha. So this is the temperature power spectrum, and this is the temperature autocorrelation power spectrum, and this is the mass power spectrum. And as you can see, the alpha quantities have a quite means influence on these parameters, and this blue one is the lambda CDM. And this is we use cosmological data sets for constraining the parameters, and this is the standard matter cosmological. This is the dark energy, this is the equation of state, and what you find that the alpha 2 is actually from data minus 1/3. So as we already explained, we expected from our analysis that the for tracking behavior to be 2, alpha 2 alpha 2 has to be less than minus 1/3, which is also true from the cosmological data analysis. And this is another thing we showed, that if you don't consider the perturbation of the quintessence to plot this temperature autocorrelation function and the pk, you can get these overshooted solutions. They are very different from there. So generally people do not consider the perturbations, but one should consider to put a better constraint. Otherwise the constraints may be misleading on the cosmological parameter. So what is the summary here is that we studied the tracker quintessence model with a general potential, and we found a general condition for the tracking behavior, and we showed that the linear perturbation can affect the cosmological observation, and actually you can see that those alpha parameters are called active parameters. There is only one active parameter which can generate the tracking solution, and as I mentioned that the perturbation should be considered. Now let us take the phantom case, which is in phantom case, why it is called phantom. Here the kinetic energy of the scalar field is negative. So for quintessence, the field will roll down through according to the slope of the hill. Here it will roll up because the kinetic energy is negative. So you can consider that, and you can find the Friedman equation in a similar way, and just you can do the same kind of transformation. But here you have to be careful about considering the hyperbolic function rather than the polar coordinate. You have to consider the hyperbolic coordinate, and you got the same set of equations. Now, in this case, actually, we divide our dark energy sectors into two different parts. One is that this V pi, we write a constant part and the evolving part, which is without any loss of generality, you can write. And this V0 can be treated as a cosmological constant. So in our dark energy sectors for this work, actually consider we have the cosmological constant and we have the scalar field. So there are two components. So it is a multi-component scenario for the dark energy. And again, we consider the perturbations, and it has bit of mathematics to calculate these quantities. We have to do it. And then you can find a similar way the fixed points, and you can find this is the tracker condition, provided that the alpha 1 and alpha 0 are 0. So you can just write down the tracker situation here. And similarly, to put it in the for the numerical simulation, you have to find the initial condition, which is also can be done using the tracker condition like the quintessence model. Here we show you the plots, and this is for the only phi. That means this is the scenario when this is a single component and only scalar field, and you can see these are all solutions. They are merged together. It's evolving in a similar track, but very recently, depending on the choice of their alphas, they actually are differentiated in the late time. You can got different evolution, but it was following the same track for a long period of time. And here actually this is the phi plus lambda case. Here you can see that for different choice, this is the omega, and this omega actually have two different one contribution. This is the total one. This is I think this is the omega phi, and this is the lambda case. So contribution from the lambda, and this is from the scalar field, and you can just add them up to get this one, if I am not wrong. No, this is the actually total. This is the contribution from phi, and this is the contribution from the cosmological constant. And this is the similar plot. This is, you see that almost they have the same behavior. Even you have a cosmological constant there. And here is the kind of a phase plot for this one. Here for the phantom, you see the perturbation won't have much effect on the cosmological parameters. So for the contrary to the quintessence case, phantoms does not affect the perturbation sector very like the quintessence. This is also another finding. And now we consider the data analysis with different kind of data like the CMB data and the supernova data, BAO data. What we find that that consideration of the phantom model can increase your value of H0. So if you remember, I was telling that the H0 from the CMB is around 767, but here if you consider the phantom, it can go a bit higher, around 69, but it cannot solve the cosmological Hubble tensor, because the Hubble tensor has this value of the Hubble parameter to be around 72 or 73, which is, so you can increase with the cosmological phantom field a bit, but it is not enough to solve. And here also you got the constraint on the parameters, and it also says that the alpha 2 follows the condition we find for the tracker behavior. And this is kind of a plot. This is the table for the best fit parameters which we got from our analysis for different models. And last three models are actually having cosmological constant plus the lambda for different combination of alpha 2. So if there is alpha, that means all alphas are varying as a parameter. If there is alpha 2 only, so that means alpha 0, alpha 1 is 0, and only alpha 2 is varying. and this extended means we have a range of prior is much bigger than other. So what we found here is that tracking behavior of the phantom field is kind of for a general parameterization, and we also consider a linear density perturbation from the phantom field. And another condition we found that the scaling solution which I mentioned for the quintessence is not available for the phantom model. We showed three different models. One is the cosmological constant, another is the only scalar field, another is the scalar field plus cosmological constant. And we found that you can increase the value of the Hubble parameter a bit, but it's not enough to solve. And here, as I mentioned on this plot, that you can get for omega lambda, so you can get a negative contribution, like here on this plot you can say you can get a negative contribution from the cosmological constant. So your dark energy sector could be more involved, and basically you can get a scenario in which your dark energy sectors have multiple components, and even you can have the cosmological constant, but that in that case the cosmological constant has to be a negative value. But if you have only cosmological constant, it's the contrary, you have to have the cosmological constant with a positive value. And as you can see, these two models, even the quintessence, which I forgot to mention, cannot solve the Hubble tension and the phantom. So what could be the other possibilities? Like as I mentioned, the dark energy sectors could be more involved. You can have more than one component, and they have complex dynamics. And other thing is that you have the dark matter and dark energy. They could interact with each other in some way, and they can give you some solution to the Hubble tension. And then there are some interesting but unpopular work is like the cosmic void, that we are living in a cosmic void, in which if we are in a void, you can see so that this accelerated expansion is a kind of a natural phenomenon if you are living in a lower density compared to the other places. And another unpopular is the concept of multiverses like that, and you could have the screening mechanisms. So all these things are like people are trying to solve these tensions with many by proposing different kind of models. And another way is that you can have the modified gravity models. Why you can have modified gravity models? That the gravity is not proved at all scales. You have tested the gravity at the only R. If it is strong gravity regimes, the GR performance of GR is not good. You need corrections. And late time accelerations need new physics, and constructing the quantum gravity theory is also you can have you might want the modified gravity models. And these are the few, just to mention the modified gravity models, which are FR and scalar tensor theory, Gauss-Bonnet theory, and these are the very complicated models. And this is the kind of landscape for the modified gravity model. So that's another option for the solution for the accelerated expansion and the current tensions. And what is the current status in cosmology is like a jigsaw puzzle, where you generally, what is happening, you fixing one thing and you just break something else, some other observation. So that's the current status. So it's very open and very exciting time in cosmology to work. And thank you for listening to my talk. I would like to finish here, and if there is any question.
Oh, okay. Thank you very much, Nandan.
Thank you.
Any question from students? Anything to, well, you can ask anything about cosmology, definitely. No? Okay.
Um, if I remember correctly, there are many ways to input the potential, like we can put the scalar fields, vector fields, or maybe tensor fields. So I would like to know why you use the model of scalar fields. Have you ever tried the vector fields or maybe tensor fields?
No, I have not tried vector field or tensor field. I just tried with the scalar field, and the quintessence and the phantoms are the most popular and the kind of easiest choice for the as the candidate for the scalar field model.
Anything else that you, no? Do you get the answer? Maybe.
Yeah.
Okay. Okay. So, okay. Any other questions? มีคำถามไหมครับถามภาษาไทยก็ได้เดี๋ยวผมแปลเป็นอังกฤษให้ No. Well, I have a question actually. So, well, I, well, and well, to be honest, I'm not working on this kind of field, right? Well, but well, at the very end, near to the very end of your presentation, you mentioned about some other possibility, right? Might be the answer of this current issue,
Yeah, yeah,
right? Like a multiverse here.
yeah.
I'm very curious. What can you explain again about this multiverse perspective here? If there is, if there, well, if there are some other universe actually.
Yeah, actually, I am also not very expert, but I on these things. But these are the kind of unpopular ideas people suggested that during the inflation you can have like a bubble universe. From one of us is from one expansion of the one point of the universe, and somewhere from some other point at the beginning they expand to give you another universe, and might be the physical laws are different like that. So means, frankly speaking, I also don't have much
All right.
expertise on those things,
Okay.
but yeah, people claim that they could be the answer for the
Okay.
accelerated expansion.
But this is very interesting point of view
Yeah, yeah,
because,
yeah, yeah,
well,
yeah.
anyway, in the next slide, you also mentioned
Next,
about yeah, this
yeah,
modified gravity here,
yeah.
right? Well, this I believe that this is another way to solve the cosmological constant issue, right?
Yeah, yeah.
Okay, so it seemed to me that you still believe that actually GR is still correct in some regime, but as
Actually,
you reply there,
yeah, yeah,
in a strong regime is it might be needs some correction, right?
yeah, yeah, yeah,
That is the reason why the modify, right?
yeah, yeah.
Okay.
This is the yeah. Please.
Okay, please. What you're going to say?
What my point is that the modified gravity models are there, but if you want to satisfy the local observations with our solar system and other local objects, then you can show that the modification from the departure from GR is very small,
Okay.
quite
So,
small. So that's
all right.
why sometimes people are not interested about the modification of GR.
So my okay. This maybe leads to next my next question about this uh, gravity model here. Um, what is it possible to have like a new theory actually to be, well, to replace Einstein general relativity completely, in order to solve this kind of issue, because it seems to me that actually this kind of issue is still persists some way or another. Whether you modify the theory of GR or you try to solve many way, right? It still persists somehow. You cannot solve it, right? And then definitely you cannot have a theory of quantum gravity somehow, because it seems to me that somehow you need a new breakthrough or a new theory which is actually not general relativity, or it might be something totally different, right? But it's much more fundamental.
Yeah,
Is
yeah,
that
yeah.
possible to have
Yeah,
that kind of
I think we should not rule out that possibility. Maybe someone can come up with some idea of
mm,
modified gravity, which can solve all many problems, which like the because if you consider the modified gravity model, so you don't have to consider the dark energy, which is kind of an
mm,
exotic matter you consider to be in the universe. So if you can get a theory of gravity which is better than the Einstein gravity to explain. But
mm.
unfortunately, still now the Einstein gravity is the most successful one we are having.
Okay. All right. Okay.
But that
Okay.
possibility is
Yeah.
okay.
All right.
Someone can come up
Yeah. I
sometime, I
hope
think.
that one of
Okay.
them in this room might be the one who discovered
Yeah.
that new theory.
Yeah.
This might be you, right? All right. Okay. Anyway, thank you very much, Nandan, for this
Yeah. Thank
wonderful
you.
talk you gave. Well, this kind of this student a whole a new arranged arranged perspective on this cosmology, and then there are still a number of open questions actually.
Mhm.
If you this
Mhm.
guy are interested in, and they can jump into
Yeah,
the
yeah,
field and try to
yeah,
solve them. Okay.
yeah, yeah. Yeah,
Anyway, thank
please.
you very much. Okay.
Thank you.
Bye.
Bye.
Okay.
Bye. Thank you. Thank you.
Okay. Have